let's continue the lecture last week, and we introduced the opacity and the transparency, and also the brightness temperature for the atmospheric constituents, and we get expressions to how to calculate the brightness temperature. So now for this lecture, first we want to introduce is the emission by the clear atmosphere. Clear atmosphere first. So the first way is if we have an up-looking radiometer. So looking radiometer, this one on the ground, okay. So we have the atmospheres, the layers, the atmosphere, okay. So this is the top of atmosphere layer. So for each atmospheric constituents, it has the emission, all right, detected by the radiometer, and it can be the brightness of it can be defined as downward, all right, because it's downward emission to the up-looking radiometer. So it is related only to the theta, the elevation angle. So here is the elevation angle, plotted like this one. So this is theta, right? So we can express it as the downward emission by the atmosphere. So it can be expressed as Tdn. It equals, as we mentioned previously, it is related to the absorption coefficient, right? By the atmosphere to the electromagnetic waves, and also related to the temperature of the atmosphere physically, and also it is related to the opacity of the zenith opacity, right? So minus 1 node, 0 theta, and considering the oblique or the zenith elevation angle or zenith angle, we have a sec theta, right? So it is an integration of it from here is theta equals 0, and here is theta equals, we define it as infinity, okay? So it is 0 to infinity, and further here we have constant related to the zenith angle. So this is the expression for the downward emission by the atmosphere. So this is downward emission by the atmosphere. However, if this is the downward emission by the atmosphere, but it is not the detected signal by the radiometer. Why? It's because we have several other emissions. They were emitted by the cosmic and the galactic from the space. So we have emissions from the space. This one. It is composed of the cosmic or galactic emission. So it propagates through the atmosphere and then arrives at the radiometer, and we take it as expressed as T extra, the brightness temperature of the emission. So it is composed of the cosmic plus the emission by the galactic. Okay. Okay. So now we wanted to define the parameters for that one. So this one is the absorption coefficient, right, by the brightness temperature as we introduced last week. Absorption coefficient. And this is the temperature, or the thermometric temperature. Okay, and this is the Venus opacity. All right. So from this equation, we can see that the emission by the atmosphere is highly related to the absorption coefficient. So that means if the atmosphere, if its absorption is very high, that means its emission is very high also. So they are in a positive proportional, not proportional, but they are in a positive relationship, right? So that means if we wanted to express the emission by the atmosphere, let's plot it. So, as we mentioned previously, we have the expressions. This is the frequency, and this is the brightness temperature or emission. So we have two peaks in the range to 90 gigahertz. Okay, this is 0. From 1 gigahertz. So we have two peaks for the water vapor and two peaks for the oxygen, right? So this one. Like this one, right? So this one and this one and this one are for the water vapor, and these two are for the oxygen. So this is the brightness temperature or emission by this one, and it follows the same shape with the absorption loss due to atmosphere. If you look back to the lecture notes for last week, you're gonna find they have the same shape. So now, if we wanted to, let's come back to this one. So if we wanted to calculate the total emission detected by the atmosphere, detected by the radiometer, it can be expressed as T, the downward emission by the atmosphere, plus the downward emission by the cosmic emission and the galactic emission, and so there's both of them together. And also, besides that, we have another term is related to this term. So it's E minus node again sec theta. So this is the emission by this one. For the calculation of the brightness temperature detected by the radiometer. Okay. Now, if we wanted to do that further, and we wanted to express the some other hydrometers detected by the atmosphere. So previously we introduced that the absorption coefficient is mainly caused by the water vapor and by the oxygen, and so this is just a homogeneous or roughly homogeneous medium detected by the radiometer. Sometimes we will also want to monitoring the weather conditions, right? For example, the rain, the cloud, the fog, and the snow. So that means in the atmosphere we have some other hydrometers inside of it. So there are many hydrometers, all right, inside of it. So it can be rain, can be snowflakes, can be fog droplets, can be haze, or can be cloud. All right. So that means there are many droplets inside of the atmosphere. So our detection cannot be used to this question only. So we need to include many other emissions by the hydrometers. So for now, we wanted to calculate is the or introduce the extinction by hydrometers. Okay, so for the hydrometers, it is involved only the two parts, two mechanisms. The first one is absorption, and the second one is scattering. So the absorption, second one is scattering. So because they are distributed inside of the atmosphere, so what we needed to consider is we needed to include several parameters. I'm not sure whether you remember that when we try to introduce the atmospheric constituents, the absorption coefficient, we named that they have a ratio, all right, for the oxygen and water vapor inside the atmosphere. And we assumed that, or it is usually assumed that from the height from 0 to 32 kilometers, the ratio keeps constant, right? So that's why we can use a fixed theoretical model for the calculations. We do not need to change the parameters such as the ratios, the volumetric contains, something like that one. But for the hydrometers, we needed to consider that. So that means we need to consider the first thing is the shape, all right? The shape of the hydrometers. For example, for raindrops, or for the fog droplets, or the cloud droplets, we usually set it as a sphere, all right? And for the snowflakes, we may consider it as disk. And for the rain lines, very heavy rain, all right? We can regard it as needles. So this is the shape of the hydrometers. And also we need to consider as the density, all right? So, or the number. So we keep it as parameter density corresponds to the number of in the unit volume. And the third one is, even though it has the shape and the density, It has another one, the size distribution. Because in a fixed geometrical location or at a specific time, its shape or its size is not constant, right? It varies from smaller one to the greater one, and it cannot be a constant or a fixed value here. So we need the size distributions for the calculations. The fourth one we need to consider as, because we wanted to analyze the interaction of the electromagnetic waves with the hydrometers, so we need to know the one parameter that we usually need is the dielectric properties, right? Properties. So we need to consider all these parameters for the calculation of the extinction by hydrometers. So it becomes a little bit more complicated, right? So now we assume that there are several assumptions. So the first assumption is that the distribution is random, so a randomly distribution. So for the random distribution, that means for our scattering, for example, if we have several droplets, so we have a coming ray or instant ray, each scattered by this one and scattered by this one, and comes to the radiometer like this one. And so what our consideration is, another one is maybe comes from the scattering of directly comes to here. So that means if they are randomly distributed, so we can assume that the contribution by all the hydrometers, are incoherent. This is very important. So we can just add all of the amplitudes detected by the radiometers together algebraically for the calculations. We do not need to consider their phase, because the distribution inside the scattering inside of the volumetric scattering is complicated, so we do not consider it incoherent. And so this simplifies our calculations very significantly. All right. So the third one is we usually consider the shape to be spherical. Some guys are going to question that. How about for snowflakes? All right. For snowflakes, they cannot be regarded as the sphere. All right, it's because it is a piece by piece show that looks like the discs. So how do we assume it to be spherical? That's because according to many investigations, it is found that the shape of the snowflakes has negligible influence on the total scattering effect. So we usually regard these snowflakes, the shape of snowflakes, to be spherical. So that means that we can use scattering or the radar approximations for the calculations. All right. So we know the when we know the important parameters that we need to include in our calculations, and we know several kinds of assumptions for the calculations or for the theoretical modeling. What we need to do next is we need to obtain some parameters that can be used to represent the scattering or the absorption by the hydrometers, right? This one. So we need to further investigate this part. This is what we wanted to introduce is the interactions of that with the hydrometers or the spherical particles. And so firstly, let's assume the instant power density So the scalar part of the Poynting vector, right? We name it as SI, instant, okay? And the absorbed power, or the power loss due to absorption by the hydrometers, we call it capital P, A, absorption, right? So now we have a parameter that is very important for us as the it's related to the absorption. So absorption cross section. The cross section is popular, right? So for example, for a sphere, its cross section is around A equals pi times if its radius is r, all right? Pi r squared, right? The cross section of the spheres algebraically, but for the absorption cross section, we use another parameters qa to represent that, and it can be expressed as the power, the absorbed power divided by the instant power density. All right. So S unit could be area. All right, m squared. So this is the cross section. The absorption cross sections for the caused by the hydrometer. So this is, we need to take care as that this is for individual particle. All right, for an individual, not for all of them. Right. So this is the absorption cross section. Another parameter that is related to is the absorption. We really want to have the efficiency, right? We have the efficiency. And we use psi to represent that. Psi equals QA divided by the algebraical or the algebraic cross section. So it can be expressed as QA divided by pi, smaller case r squared. This one. So this is for the absorption. As we mentioned previously, it has two basic mechanisms, right? The first one is absorption. The second one is scattering. So for scattering, we have the expression as PS, the scattered power. So it should equals the power density, scattered power density. It's related to theta and phi in a spherical coordinate system, and should times the area, right? So area over the whole solid angle for integration of 4 pi. All right. So now we can get the cross section for scattering. So this is again scattering cross section. We call it QS. S divided by the SI also for the PS, right? So the psi S is expressed as QS divided by pi R square again. Alright? So this is the for the scattering part. Now what we want to do further is for the power, for the instant power, so we use PI, instant power. So it is there as power loss due to absorption and also the power due to scattering. Alright? And is there any other parts for that? There is no other parts because some guys gonna question this. How about the power detected by the receiver? Actually, this one is related to, it is contained inside of the scattering power because it is composed by two parts. The first part is backscattering. Detected by the radiometer, right? The second part is the diffuse scattering. Or the diffuse scattering. Another one is the forward scattering. So for radiometer, we use the backscattering, all right, or the radar system, and the forward scattering is we use the for the wireless communications, the receiver detected by. Okay, receiver. And the diffuse scattering is regarded as loss, correlated. So we don't consider this part anymore. So that means now, if we wanted to detect the total extinction, so it is composed by two parts, right? The absorption and the scattering cross sections. And also for the efficiency, the total extinction is equals psi A plus psi S. So for here. So some guys may question how we could separate these three parts away. So we can consider the condition like for the backscattering, that means if in a spherical coordinate system, backscattering means the theta equals pi, right? Forward scattering means theta equals 0. So the diffuse scattering means theta larger than 0, smaller than pi. Okay. So in our calculation, we can use the elevation angles to separate the different scattering mechanisms. So for the radiometer, we are more concentrated on the backscattering, right? So we use the power density as SB. It is related to backscattering, the instant power density times what? A term here, sigma phi. Sigma b is called the back scattering cross section, and divided by the distance between the radiometer and the particle. So it's 4 pi, the solid angle of the whole, r squared times. Okay, so this is the power density for backscattered powers. So otherwise, if we measure the power density due to the backscattering, we can calculate the cross section. It can be related to 4 pi r squared times SB divided by SI. The same form with respect to our previous equations, right? So this is the cross section, and the efficiency, it is called psi b. Again, it equals the cross section divided by pi r squared. This smaller case r is the radius of the hydrometers, right? And the capital R is the distance between the radiometer and the hydrometer. So this is the expressions for the some specific to characterize the absorption, scattering, and the extinction. So for further calculations of the theoretical modeling, we needed to include is another term. So before that, we needed to concentrate that. I think most of you may be looking at, say, the expressions for the theories or for the theoretical models due to scattering. So here is the backscattering efficiency, and it looks like this one, right? The expressions, and we usually name this region as the Rayleigh region, and this region is me region, all right? And also over the height forward to, and here we already call it as an optical region. So for the x-axis, we already have a parameters called chi. The chi is represented as 2 pi r divided by lambda node. So that means here, look at this parameter. We have the small case r as the radius of the hydrometer or of the particle, individual particle. And here is the wavelength of the electromagnetic waves, all right? So chi represented the ratio between the radius of the particle with respect to the wavelength. So this is a very important parameter, and it has a name. It is called normalized. Circumference. So for a general expression, it can be expressed as kappa, and it is expressed as 2 pi r over lambda b. So lambda b is the wavelength of the electromagnetic waves in background media. So I think you guys know. For the hydrometers, the background is just air, right? So the lambda b can be equals lambda node, the wavelength in vacuum, right? Because it can be further represented as 2 pi r, or lambda node times square root epsilon b prime. So for air, epsilon b prime roughly equals 1. All right, so it is related to this expression in air, for air. If, for example, we have some other calculations on the volume scattering, such as the particles in a uniform medium, such as in the ground or in soil, there are some maybe the solids particles inside of it. The background is the soil, so the epsilon b prime cannot be equals 1. It has its own values. And now, if we know these ones, so we wanted to further for the calculations. So the first thing is we consider the mean theory. So for mean theory, that means it's the separation point from me and the Rayleigh as chi equals 1 point note here. So for here is 0.1 maybe, and in this region is around maybe 10, like this one. So when chi is smaller than 1, so that means the radius is smaller than wavelength. All right. In this region, in mean scattering theory, as the radius is larger than the wavelength. So this is the separation between the Rayleigh scattering and mean scattering. So firstly, we would concentrate on the mean scattering. So for mean theory, so for mean theory, we usually have the I will just show you guys the solutions for it. The first one is, as we mentioned, is the efficiency due to scattering, right? Can be expressed now as the refractive index and the chi, okay? And then it can be expressed as 2 over chi square, and the sum of it is L equals 1 to infinity, and 2L plus 1 times EL square, the absolute value, and BL square, absolute value. So this is the for the scattering efficiency, and then we have the name for the AL and BL, right? Only difference here. So they are called mean coefficients. Yeah. So chi, it can be obtained when we know the radius of the particles and also the wavelength, right? So what we wanted to calculate is just the mean coefficients, the most important things here. So actually, the mean coefficients, it involves the this function, and we're going to introduce that later. Another term is the extinction efficiency. It can be expressed also 2 over chi square sigma L equals 1 to infinity 2L plus 1 times the real part of AL plus BL. Okay, so and for the absorption efficiency, it can be expressed as its extinction efficiency minus scattering efficiency. This one. So we can get the expressions for these two terms. And now, how to obtain the mean coefficients. So for the when we set the assumption that for each particle, they gonna suffer the because they are individual particles, so they do not have multiple scatterings. So we just consider the single scattering only for each particles, and we can get the solutions for the mean coefficients as for AL and for BL. So for AL, it has a complicated expression as AL divided by N plus AL divided by chi times WL minus WL minus 1. For this part is AL divided by N plus L divided by chi times the real part of WL minus the real part of WL minus 1. So how is about L? L is also a parameter. Omega WL can be expressed as the form as related to a cascaded equation. A minus 1 minus WL minus 2. So W node and W1, it has its minus 1. It has its own expressions as sin chi plus J times cosine chi. And W minus 1 equals cosine chi minus J times sin chi. So this is for AL, and for BL, it has its own solutions here, and now it becomes its N times AL plus L over chi, and times the following terms, identical here. Okay, and also this side is AL plus L over chi times these things. Also, I don't want to try and to write that things. So here we need to consider is N. N is not a number. It's related to the refractive index. So N is the refractive index, and it has mostly for dielectric particles, it has a real part and an imaginary part, right? So the real part is related to the real part square root epsilon, like this one, and the imaginary part, it is the imaginary part of the square root of epsilon again. Here is minus. So, all right. So we introduced this part very early. So if we know the dielectric constant by the, for example, the materials for the hydrometeors, for example, for rain, the dielectric water, all right. For cloud and fog also, for fog also. For cloud, it may enclose ice, so dielectric of ice. And for snow, it is a little bit complicated, right? Because for snow particles, it has ice inside of it, and also it has air, right? It has some ice, yes, and also for the wet snow, it has water inside of it. So it is composed by three components. They have their combination with different ratios, right? All the volumetric components inside of that. So now this is for the absorption and for the extinction and for the scattering. And also we have another one is for the back scattering. Okay, so we're gonna introduce this later after the short break. Now let's take a short break. So for the backscattering coefficient, or for the backscattering efficiency, it has its own expressions by the cross-section divided by pi r squared, and equals -1 to the power l times the summation of l corresponding to infinity minus sorry, it's -1 should be inside of it. This one beside h times 2l plus 1 times al minus bl, and absolute value of square, and here is 1 over chi square. Here is 1, okay, not 2. And so this is the expressions for the backscattering coefficients. And this is just for the so this is for the misscattering, and later we want to introduce that to the Rayleigh approximation. So for Rayleigh approximation, it is under the condition that when we assume when the refractive index times the normalized circumference, the absolute value of h, we already set them to be smaller than 1 here. And this we can use the Rayleigh approximations. And the solutions for the scattering efficiency is equals h over 3 times chi to the power 4th times k absolute value of h. And it has the second term, third term, okay? And we do not take that one. And the k is a complex quantity. So for the complex quantity, it is related to the equals the refractive index, related to that one, and also related to n square equals epsilon minus 1, epsilon plus 2. So related to this because epsilon is complex value, right? So this one is complex quantity, and this is for the scattering. For the extinction is 4 times chi times I, and the imaginary part of minus k plus h3 chi to the power 4th k squared, like this way. So that means it's some smaller values of terms. So what we can see here is when we compare both terms, this is scattering. It contains inside of the extinction, right? So the absorption is the extinction minus the scattering, so it equals 4 times chi imaginary part of minus k. This is the calculations on that one. And also, we can get, because this is the efficiency and the cross section is equals 1 square over pi times chi to 3 imaginary of minus k absorption. For the scattering, that's 2 square over 3 pi squared times chi to the power 6 times minus k. Okay, and so from here, when we come to compare that, there is one comparison I want to introduce you guys is this one. So we can see for the absorption part, it's related to the cube power of the chi, all right? And for the scattering as the 6th power of that. So that means what? So we can get a conclusion from this one is that this term, because it's related to the chi equals to pi r over lambda node, right? So as inversely related to the wavelength. So that means QA, which is much larger than QS. This is for the Rayleigh approximations. Okay, for radar approximations, the absorption plays the main role and should be suppress the scattering calculations. So if we want to plot the terms of that as just chi here. This is the sign. Okay, it can be extinction, can be absorption, and it can be scattering. So here as first layers, the scattering it really looks like this one, and so this is psi s, and the absorption it usually follows like this one. Absorption. So in the lower frequency regions, or in the radio regions, the absorption is much larger than the scattering. And when it transits to the missed scattering region, it should be sometimes lower than the scattering loss. When we, for example, to calculate the what sorry, should be named this region here. It is 1. When we to calculate the scattering by the wet snow and dry snow, for example, for dry snow, we really get the scattering loss is higher than the absorption loss because the snow particles exerts the higher scattering loss on the especially in the terahertz waves than the absorption loss. So we named here, we have a condition that n times chi is much more smaller than 1. Actually, here, the separation between them is named at 1, alright? So we take a more general condition for the separation of the relay and mean this range, this separation is n times the refractive times chi is smaller than 0.5, then we can use relay. If it is larger than 0.5, we can use mean scattering. So this is the separation here. And so for the radiometers, we are more concentrated on the backscattering. The backscattering for this one is 4 times chi to the power 4th times k squared. So under the condition that n times chi is smaller than 0.5 here. So if, for example, we wanted to concentrate it as the refractive index is very high, or the dielectric constant is very high. For example, the conducting spheres or the conducting materials, we assume that the refractive index or the absolute value it is much larger than 1, alright, for the conducting materials. And but it cannot be infinity, alright? It is finite. So that means when we come back to here, the conducting of n is the refractive index is much higher than 1. So this term is roughly equals how much? This is roughly equals 1, alright? So that means the k equals to 1. So psi b equals 4 times chi to the power 4th. This condition. Alright? So sometimes we wanted to say as if the condition, under the condition that the conducting spheres is satisfied, also the refractive index is related to infinity. And also as chi is much smaller than also, and we can have the another expressions for backscattering is 9 times chi to the power 4th. And the calculation is very complicated, so I will not show this one here. And so this is the expressions for these two conditions, this one and this one. So now we just characterize the efficiency for the extinction, absorption, and scattering with respect to the chi. All right, chi is related to the wavelength, as we previously mentioned, equals 2 pi r over lambda naught, and also it can be expressed by the frequency. So there's frequency dependence like this one. So UP as the phase velocity for the such as for the plane wave, all right, phase velocity for a large propagation distance. So now it is related to the frequency for the electromagnetic waves, and we can get the expressions or the calculated expressions for it, all right? Because when we are doing the channel modeling or the radar systems, the theoretical calculations, we are more concentrated on the frequency response instead of the wavelength response, right? So now we finished the solutions. We get the solutions for the cross section of the extinction, absorption, scattering, also the related efficiencies. Another thing that we need to take care is here we use the refractive index or the dielectric constant here, all right? So we used these two terms, all right? And for the dielectric constants, we need to obtain that because it is the material dependent, right? So for different materials, it has the different values. And so now we want to introduce, further introduce is the dielectric properties of the hydrometers. Properties of hydrometers. So for these materials, we first introduce is the for the water particles. So for the rain, water cloud or water fog, so its main material of that is water, right? So for water particles, actually for the empirically, so not actually, empirically based on the measurements that in the range of the low frequency up to 1 gigahertz as dielectric constant as can be regarded as the real part of water is around 88. If it is larger than 1 gigahertz, empirically, it can be expressed as equals around 4. So this is for the water vapor. And actually, right, we usually wanted to get the exact values. And there is one theoretical model is called double Debye dielectric model. Right? So it is around, you already call it D3 or D3 like this. So we will introduce this later. So now here we just wanted to concentrate on we can just express the values empirically based on measurements. Okay, and for the ice particles, over the whole region with the frequency smaller than 300 gigahertz, the real part of ice can be regarded as constant around 3.2. We can use the fixed values always. Okay, and for the, you guys gonna be confused, wanted to know how the imaginary part is related for the ice particles also. So try to use the double polarimetric models, which we should be concentrated on that. And I'm going to introduce you guys later. So this is the theoretical models for the water particles and the ice particles. And why we want to introduce ice particles? Because we wanted to later concentrate on the snowflakes. So for snowflakes, we really separate them to be two parts: dry snow and wet snow. Alright? So for dry snow, it is composed by two parts. The first part is ice particles with air inside of it, alright? Because the snowflakes cannot be pure ice particles, alright? It has some air inside of it. And for wet snow particles, it has ice, air, and also for wet because it has water inside of it. Right? So for the snow particles, the snowflakes, one parameter that we should be very, very important is the density of ice. As rho I equals, it is constant usually 9167 gram per cube centimeter. This is for ice. However, for snowflakes, it is complicated because it has its own combinations such as the water, alright? So it changes from 0.05 to 0.3 grams per cube centimeters. So this range, for this side is related to the very dry snowflakes. For this side is related to the very wet snowflakes. So for wet snow, it has a wetness parameter. The wetness parameter corresponds to the water content inside of it, but it cannot be very high. So for example, I increase the water content inside of the wet snow particles, but it has a limit. The limit is that it should be smaller than 30%. Alright, so it's larger than 0, smaller than 30%. If it is larger than 30%, that means the snow going to be melted and it becomes a water droplet, so it becomes water as raindrops instead of snow. Okay? So sometimes when we see, especially in the spring, alright, we have the snowflakes and water droplets together, the drops, alright? That's because the wetness inside of the snowflakes is so high that some of the snowflakes becomes the raindrops, and we call it ice rain, alright? So for the why we want to use the density of snowflakes, because we wanted to calculate actually the part for dry snow. It is related to its density minus 6. s. And this is the real part, and the imaginary part is related to the real part times 0.37 s divided by 1 minus 0.46 s power square. So this is the expressions for the slope. And now we want to finish the introduction about the dielectric constants, and we want to introduce combine them to the solutions of me theory and the really approximations. So now is the extinction of hydrometeors. And extinction and backscattering. Okay, so as we previously mentioned that there is no, because for each individual particles, they have their own random distribution, and so there is no coherent relationships between neighboring particles. So we can calculate the volume scattering coefficient, right? So now, previously we just mentioned for individual particles. Here, we want to totally calculate the volume scattering coefficient. We call it kappa S. Could you remember that? Previously, we introduced, for example, for a homogeneous material, we introduced the absorption is related to the absorption coefficient alpha. All right, for a homogeneous medium, because alpha is related to the propagation constant is alpha plus j times beta, the phase constant, right? The kappa A is for the for the power is 2 times alpha. All right. So could you remember as unit? As intrinsic unit, could you remember that? So we can express it. This unit is Newton per meter. Am I correct? All right, it's Newton per meter. And if we wanted to transfer it to be the dB per meter, we should have it times how much? 3.4. 3 times 10 to the power 3 times. All right. So the transfer of the units. Okay, here we wanted to calculate the volume scattering of that one, and also in the unit of Newton per meter. But as we all know that H is related to the basic of H should be the scattering cross section. All right, and for each individuals, and we should sum of them together with respect to the radius, right? So we have the total numbers of H. All right, the total number of H should be expressed as the size distribution times dr from the range of R1, the minimum, and the R2, the maximum, right? The total number of edges, so it becomes as PR dr minus R1 to R2. So PR as the size distribution. So this is the total extinction coefficients calculated by this term, and QS equals psi s r times pi r squared, right? So if we substitute them together inside of this equation, it can be further expressed by another equation as well, the node q 8 pi squared times integration of chi squared and p chi times psi s chi d chi, and this from 0 to infinity. So this is the scheduling. Okay, now we finished this part. We come back to our previous introduction. So we assume the shapes always in sphere, right? Sphere. And we analyze the density of H expressed by rho s, rho w, all right? They are constant for rho s and rho w. Rho s, this depends on the composition of H elements. And we analyzed the dielectric properties, right? So now we're gonna concentrate on finally concentrate on the size distribution. So the size distribution expressed as PR in this calculation, P chi, right, or P chi or PR, right? So the size distribution here, size or drop size distribution. Usually, we have some most general expressions for H is the, for example, in cloud, it can be expressed as PR. It equals A times the radius of the power R exponential minus B R to the gamma. When we look at the form of this equation, all right, we really to do the fittings, we like to use the power term and the exponential term, all right? So that means this expression is just based on the measurements, to fitting to the measurements. So it is just an empirical function or formula. And we call this term as normalized. Modified. Gamma distribution. Why? Because it has its own a general gamma distribution. For general gamma distribution as R equals A times R to the power alpha, E minus B R. There's gamma equals 1. This is for general gamma distribution. Because it is modified because this term, this formula cannot compatible with a more general cloud. Okay? So now we get the X and the distributions here. And later we're going to introduce much more other, such as the log normal distributions, or the Gaussian distributions, and there are many other specific distributions also. So here we just consider the gamma distribution here, and so this distribution, it has a unit as millimeter per millimeter per meter cube. So we look at the unit. This term means it is in a unit volume. Alright? And this term means it varies in a unit radius change. So that means the drop size distribution related to the drop numbers in a unit volume and relates to a unit radius change that related to the number of the drops. So if we wanted to do as we wanted to calculate, as we previously mentioned, as NV. NV as the total number of drops in a unit volume. So that means we should take the integration of the drop size distribution with the radius, alright, from 0 to infinity. Contains all of the drop numbers, and we take expression inside of HA times R to the power R times A to the power minus B R to the power gamma times dr here, and we can get the expression is at A gamma x times gamma to the B of x, okay, x equals R plus 1 over gamma. So now we know why it is called gamma distribution, because finally we get the expression gamma function. So for the total number in a unit volume. Okay, so this is why we get that one. And another very important parameter we needed to take care as the parameter is called mode radius. It is called RC as the mode radius. The mode radius means that it is related to the when the drop size, when the drop size distribution function, it equals a maximum value. All right, as when we try to see the measurements for the drop size distributions, it follows like such a function here, right? R PR. So the RC corresponds to the maximum of this point. So when PR equals maximum, the corresponding radius is called the mode radius. So how to calculate that? For the maximum, that means the differentiate of PR equals 0, right? So we get RC of gamma equals alpha divided by B times gamma here. So this is the expressions for the calculations on the mode radius here. And so later we want to introduce as for the most concentrated for the radiometer as the backscattering coefficient. All right. So for backscattering part, and the scattering coefficient. Previously, we expressed it as sigma b, all right, for an individual part, but here we want to use it as the total, so the volume of it. So for an individual part, it is expressed as times the 64 pi to the power 5 divided by lambda naught to the power 4th radius out to the power 6th and k squared, right? K equals n squared minus 1 over n squared plus 3, like this one. So this is just for an individual particle. So for the volume part, as we mentioned, there are relationships for the scattering as incoherent. So we can just sum them together and get the total backscattering volume, backscattering, it equals the backscattering of individual parts. The sum of that is n times nv, or the total number in unit volume, right? So unit volume part. And it can be expressed as 64 pi or 5 lambda naught or 4th and k square, and the sigma of that one is just the sum of radius, right? So this is sum of radius, and its unit is -1. It's per meter here. So another thing that we want to use for the radar systems, for the actually for our radar detections, we only use the radar cross section, all right? So radar cross section RCS, and for the meteorological radar systems, we are not more concentrated on the cross section. We are more concentrated on the reflectivity. So how, if I get the cross section, how I transfer it to the radar cross section, transfer it to the reflectivity, it is defined as this part. Sigma I equals 1 to nv Ri to the power 6. So this is the reflectivity by the hydrometeors, or by the volumetric hydrometeors. So we get the relation between the cross section, the backscattering cross section, and the reflectivity. There is term of pi to the power 5 divided by lambda naught to the power 4th, and times term k squared, like this one. Okay, now we get it's related to d squared. Okay, I'm sorry about that. So that means it equals 2 to the power 6 sigma I equals 1 to the nv ri to the q. All right, and this term equals here 64. So we get the expressions for the relationships between the cross section, radar cross section, and for the meteorological radar systems, this one is the reflectivity. Relationships between them. So if you know each one of that, you could know how to transfer them between both terms. All right. So now this is for the snow particles. So because it has the cloud particles, so it has a specific expressions for the size distribution here. in cloud. Another thing is for snow and for raindrops, alright? Cloud, it has the almost identical raindrop size distributions with respect to fog. So in cloud or in fog, we can use the expressions like this one. And if we want to transfer to the rain or snow, so here, because we regard the snow to be severe, alright? So if we want to regard snow to be severe, that means it's related to melted snow to water droplets. So that means for the rain or snow, we use a parameter to characterize their strength. All right. For cloud and for fog, we already use visibility. All right. So the visibility means the correlated to the distance. All right. So for the rain and snow, we can also use the visibility, but most generally we use another term is called the rate, right? For rain, it is called rain rate. Or for the snow, it is called equivalent rain rate. They can expressed as R in the unit of millimeter per hour. All right. So its unit means the height of the rain drops to the ground and transfer to water. Right. The height of the water per millimeter for that one. So it is a more time-dependent parameter. So why we want to introduce this one? Because the drop size distribution for water and for rain and for snow is related to the rate. So this is drop size distribution. So most generally, as we usually use this one is expressed as d. Okay, the diameter to represent that is n node times e to the power minus b times d. So the parameter b and the parameter b, it has its own parameter as well, or node times r to the power minus 0.21. So this condition is proposed by two scientists. They are called the Marshall-Palmer so it is called an MP model. Okay, so also we have several other expressions by other scientists, such as by Best, a scientist, and by the Lawes person. We call it LP direct model. The difference between them is the initial number and node, and also here the initial for the Marshall-Palmer distribution, n node equals 8.0 times 10 to the power 6 per meter fourth. So the difference between them is they have their own node and they have their own expressions for B. Okay, they have their own expressions for that one. And based on that, also we can calculate the backscattering and the extinction coefficients, right? So for the extinction coefficient, we get the expressions as 0 to infinity, chi square times p chi times the epsilon e chi and d chi. So this is the extinction coefficient we usually used to represent that. And there are also many. This is the calculations for the extinctions by the Mie scattering theory and by the Rayleigh scattering theory. And also for the theoretic cause composed, there are mixed empirical expressions. It is composed by the International Telecommunication Union recommendation. So they have their own expressions, such like we call it a specific attenuation model, right? Attenuation. So we can call it alpha equals maybe A equals maybe alpha times r to the power beta, alright? So like this form. This form is an empirical expressions, and when you Google that, using the ITU-R theoretic models, you can get many expressions correspond related to the frequency and related to maybe the slant angle, for example, elevation angle, and also related to the distance and some other parameters, right? So this is based on the empirical expressions, so it lost its flexibility to fitting the hydrometeors in different regions, meteorological regions, or the different times. So the most general expressions that we only used is the calculations based on scattering extinction and the Rayleigh approximations. When we get the exact expressions for the drop size distributions, and then we can calculate and obtain the exact values of that one. So mostly we will use these expressions, even though it's going to take it's time consuming for the calculations, and it's difficult to get the exact drop size distributions, but it can offer us a much more accurate things, because we can obtain the absorption coefficients, and we can also obtain the scattering losses also. But for the ITU models, we can only get the total extinction attenuations. We cannot separate the absorption and the scattering losses. Okay, so that's all for this lecture. And for next week, we're gonna introduce the meteorological radar systems, how to do the calibrations for that one. Okay, I'm gonna see you guys next week.